name is Pallavi Batula, and this is Lab 4, Oscillations. The main purpose of this lab is to investigate the motion of a spring mass system with the mass oscillating in an arc. The goal was to determine whether the model follows the energy principle. The result that was achieved was that the system's total energy remains constant at zero, thus demonstrating the energy principle. I used Tracker to track the observed positions in the video, and I used GlowScript to build the computational model to predict and graph the object's motion. Fundamental principles. We use Newton's second law, which is defined as the system's change in momentum is proportional to the net force applied. In this lab, we have the force of the spring pulling the mass upwards and the force of gravity pulling it downwards. These two forces are our net force. We also use the energy principle, which states that the system's change in energy is the sum of work done by the surroundings and the thermal energy exchanged with the surroundings. In both computational and observational models, our system is the mass, spring, and earth, and the surroundings is everything else around it. But we are considering an isolated system, so that would mean that our particular equation of the change of energy in the system would be equal to zero. And to further specify our equation, we include the changes of kinetic energy of the mass, the changes in spring potential energy, and the changes of gravitational potential energy as well. And we also use other equations as the update formulas, such as the position update and velocity update formulas, which are both derived from Newton's second law. So when it comes to our observed motion, I use the video provided in the instructions and use Tracker to track the motion of the mass. And as you can see in the graphs above, the change of positions show a sinusoidal depiction. Moreover, we collected the object's mass, the length it stretched the spring, its initial position, and its initial velocity. And to begin the computational model, two things were done. I took the data I received and converted it into a CSV file and to make use of in my we need to solve for the period, the spring stiffness, and the relaxed length. To solve for the period, we need to understand that it is the time it takes to get from one crest to another. And I did this by finding the average of the first 3 seconds. To solve for the spring stiffness, I used the period value and used its formula, which is 2 pi times the square root of the mass divided by the spring stiffness. Then I rearranged it, solving for k. And for the relaxed length, I used the total F net, which equates to 0, but it is also equal to the force of the spring and gravity. And rearranging that, I found the relaxed length. So when it comes to the computational model, these are the initial conditions, which were calculated from the calculations I did from the previous slide, and also the masses and the position and velocity of the initial state of our mass was collected and placed in here. So I found the S value, which is the difference between the magnitude of the stretch length, and the relaxed length. And I also found L hat. Furthermore, and most importantly, I found the kinetic energy and the potential energies. And these were based on their particular formulas, and I put the necessary variables that fit into the equation. So for the very most important part is the calculation loop. We first start off by finding the force of gravity, then updating the spring force because it's not constant, and then we update the net force, then we update the mass's velocity and position. We then find the S value, the new S value of the spring, and then we calculate the change of energies through each time step. So this is the output. The model that is outputted on the left has both the ball from the observed data and the ball from the computational data. And I found that both models in the beginning, but further distanced themselves as time went on. And looking at the graphs, the observed data on the right is done manually, so it may not have been as precise as the computational model on the left is. Possible errors. In reality, the system is not isolated from the surroundings, so there will be work done by the surroundings, and there will be additional forces such as drag force. And secondly, another error would be an inaccurate center of mass placement. I am human, and I am doing this by hand, so it may not often be accurate. So the main thing we want to know is the energy principle satisfied? Yes, the energy principle is satisfied, and this is because there is no external forces affecting this isolated system. So the change in energy must be zero. Even though there are different types of energy that are in the system, the graph below shows that there is a total change of energy that is constantly zero. We also want to see a comparison between the oscillation periods of the X and Y direction, and find that the method to find these periods was done as the same method as finding the initial period back a couple slides ago. And it was observed that choosing different directions produces deviation in the period, which ultimately affects the spring constant and the graphs. showed us that there are different perspectives of these oscillations and the changes of energy that are in play, allowing us to find differences in observations in isolated systems.